Hello, everyone. Finally, I got it working. Okay, so this is an introduction to Bayesian data analysis. Sorry for the delay. I couldn't get the sound working. So the goal of this workshop is to just give an introduction to Bayesian data analysis. And originally, it was meant to be in SAS, but now the Turing notebooks are working better, so we're using those. And my goal for making this workshop was like originally I wanted to do it last year, but COVID got in the way, and this year there was a huge mess. I moved from Norway back to Finland, and I had almost no time to prepare for this workshop. So as you can see, it's a bit rushed, but the model should be working and everything should be almost, at least the plotting is a bit under the way, but everything else should be working roughly. Yeah, so I'm going to introduce you to the Bayesian workflow in this workshop, and it's it's a way of approaching statistical problems in a Bayesian way. And this workshop was originally made for Stan by Lauren Kennedy, Jonah Gabry, Rob Tanguchi, and it's most of the hard work has been done by those guys. And also Chad has been really helpful with SAS and message theory and Tor for coding up the Turing notebooks. So I'm going to first introduce to the Bayesian workflow, then I'm going to talk a little bit about doing probabilistic programming in Julia, and after that we'll go into the notebooks, and that's going to be at your own pace. So I'm gonna we have a synthetic data set about this pest control data set there. So there's cockroaches in apartment buildings in New York, and then we start with a simple Poisson regression, and then we evolve our model to more complicated ones using this Bayesian workflow. Yeah. So this is the basic idea of the Bayesian workflow. So we want to have this principled way of approaching statistical problems, and it starts with we're given a data set, and then we want to explore what are the plausible ways of how the data could have been produced. And this is the exploratory data analysis step. And after that, is the prior predictive checking. So this is how we choose priors that are consistent with our beliefs. So basically, it means that we're not producing physically impossible scenarios. For example, if we're modeling if you have a prior on the heights of people, they can't be negative or 10 meters tall or something. Then we also want to make sure that the computer is actually doing what we want to do. So in Bayesian statistics, we're sampling values from the posterior. So we're using different algorithms to do that. And we want to make sure that the algorithm is functioning properly. So that's the sampler diagnostics stage. And we'll talk a bit about Hamiltonian Monte Carlo there, which is the most commonly used algorithm for doing Bayesian statistics. And next, we want to determine we want to compare our predictive or basically want to examine how well our statistical model is fitting our data. So that's called posterior predictive checking. And then something we won't be covering in this workshop, but once we have a lot of different models fitted to the data, then we might want to choose a model that has the best predictive performance for data that's not been seen yet. So this is like the basic structure, and next we'll go into a bit more detail. So yeah, check if there's any questions. Okay. So when we're doing Bayesian statistics, we're building a probabilistic model for the whole data. So usually people think of it as a prior and a likelihood. So the likelihood is familiar from other like frequency statistics as well. So that's given a parameter, what kind of data do we produce, and the prior is like our belief on the parameters. So that's a probability distribution. But this is like not the best way to think about it. So actually what we're doing is we're modeling the whole joint distribution. And there's a paper that explains this. So yeah, so this is the first term on the left-hand side is the joint distribution. So we have some data that's observed. So for example, we measure the heights of people, and then there's some parameters that are not measured, or they're like latent variables in the model. And this is you can factorize it as a likelihood times the prior, which is what I talked about previously, or in this other way. And there's sometimes where, or I guess historically, people wanted to use like uninformative priors, or really like vague priors that didn't give a lot of information about the parameters, or they, yeah. So, and then there's also these things called improper priors, which are like not actually probability distributions. But there's, in general, we want to have as informative priors as we can like get, or like it, but yeah, or it'll become more clear when we talk about prior predictive checking. But we want to like not allow impossible values, but still like encode the knowledge that we have, or prior knowledge we have about the phenomena that we're studying. And the nice thing about Bayesian models is that we can always generate data. So if you have a prior distribution, we can sample values from it. So we can sample this theta star from the prior distribution, and then we can feed it into the likelihood and get more data. And then so the y star is sampled from the data distribution. And now we're going to be I'll give you an example of this like Bayesian workflow. So this is an example from a paper explaining this Bayesian workflow. I have a link in the repo, but we have this pollution example. So we have satellite measurements about pollution, and they're like distributed over the globe, and we have like different countries have different amounts of pollution. And so the first step is exploratory data analysis. So we just take a look at the data and see if we can, like, what are the plausible ways of how this data could have been generated. And in this case, there are different clusters for the different countries. So there's like Europe and Asia, and like high-income countries and low-income countries, and so on. But we can, there's different ways we can cluster it. So there's a word, like you can cluster the regions by like countries, or like regions that are established by the World Health Organization, or you can categorize them by clustering the data. So you get different kinds of models. And now you can get, so you can model it as a linear regression by just not taking any categories or regions, or like, or you can, you can basically get make different models for the data. This is not, the specifics are not that important. But the next step is prior predictive checking. So this is the step where we basically determine like what do our priors imply in the model, and that. So once we choose a prior distribution, we have these parameters on the priors, which are called hyperparameters, and depending on what those are, it affects what kind of data we generate. And this is something we can do before we even observe any data. So this is completely synthetic data. And the main idea behind this prior predictive checking is to like not allow like completely unrealistic values. So we want to have probability mass that covers the sort of values that we might come up, that we might measure, but not allow like completely unrealistic values, or like have really low probabilities for them. So in this example, we have like really dispersed priors, and the data that's generated is really like spread out, or so if we then actually measure the data, we see that it's like completely unrealistic. So it's 2 orders of magnitude off on the log scale. But then this means that we can still do inference, but it's really like it's not a good idea, because then we have to have a lot of data to overcome the prior, and that's not useful. So if we have more realistic priors, we can see that they are more sort of in line with what we might actually expect to get to measure. So the way we actually do Bayesian inference is use these Markov chain Monte Carlo algorithms. So we can sample values from the posterior, and there's, let me see if we can get here. Okay. So basically the idea behind Markov chain Monte Carlo algorithms is that we have here we have a probability distribution, and we want to sample values that follow this distribution. And there are various different ways of doing it, but the idea behind Markov chain Monte Carlo is that we have this stochastic process which is called a Markov chain. So it's like a stochastic operation that only depends on the previous value of the chain. And the idea behind these Markov chain Monte Carlo algorithms is that in the long run, it will the Markov chain will converge to this distribution. And then the way we do it in practice here is this example is Hamiltonian Monte Carlo. So this takes into account the gradients of the distribution. So it explores it quite efficiently, and that's why it's commonly used in the basic probabilistic programming packages. Okay. And finally, once we have the posterior, we can do posterior predictive checking, which is a visual way of comparing the predicted data that we get from our model against the actual measured data. And formally, we can get the posterior predictive distribution by integrating the parameters out from this product of distributions. And this is really useful because we can if you're overfitting or misfitting the data, it will be obvious in the plots. And the way we can sample values from the posterior predictive distribution is we sample values from the posterior first. So this is where we use the Markov chain Monte Carlo, or this is usually we code up our model and then we use Turing or SAS to sample values from the posterior. And then we use those posterior values to generate more data. And this is now the predicted data. So this is taking into account the measurements we have. We first infer the parameters and then we generate more data. So now we have a sample from the posterior predictive distribution. And we can compare this against the actual data. So in here, we have the actual data, or the observed data in this is black line. And then we have a lot of samples from the posterior predictive distribution here in the in the blue line and the red lines here. So we can see that the model 3 is fitting the data a lot better. And we can also do this with statistics. So we have some function of the data. And in this example, it's the skew of the data. And we can see how well the model is performing on this test statistic. So again, we see that the model 3 is performing a lot better. And then you can also do it by the clusters or the categories. Same thing. Yeah, I think that's about it for the Bayesian workflow. Are there any questions about that? Yeah. apparently not. Okay, so finally, we'll talk a bit about doing probabilistic programming in Julia. So basically, one of the biggest advantages of doing this in Julia is that we can, instead of having like a big monolithic package like Stan, we can decompose the problem into smaller packages because we have multiple dispatch and they just work nicely in these smaller packages. So here are some examples of these building blocks for probabilistic programming. So we have MCMC samplers. So these are the Hamiltonian Monte Carlo packages. We have dynamic HMC and advanced HMC. And you can just use them on your, you can like code up your own like your own model by hand without using any other package, and then you can just sample it with these packages. And because we're using, we need gradients to compute these, to use the Hamiltonian Monte Carlo. We usually use some kind of automatic differentiation package, and there's plenty of those in Julia. And this is, I feel like, the biggest advantage over like PyMC or Stan, because what this makes it possible to do is separate the sort of Bayesian statistics package from other packages. So if you want to do differential equations in Stan or PyMC, you have to build it on top of their own like automatic differentiation framework. But in Julia, you can just use the differential equations package or like neural network package or whatever you want. So you can use the right tool for the job. And then we have these parameter transformations. So we usually want to do the sampling in unconstrained space. So if you're sampling, say, like a beta distribution, it's on an interval, but you want to do the Hamiltonian Monte Carlo in the unconstrained space. So you need these transformations, and there's a few packages for those. And then we have domain-specific languages, or these for actually constructing the like statistical models. And SOS is a nice example, as well as dynamic PPL, which is what Turing is using behind the scenes. And then this Bayesian workflow is based on like plotting, or like you can evaluate your diagnostics about your model visually. So there's Iris for doing a lot of those plots, and then there's the Bayes plot R package, which is used in this workshop, they have overlapping things, but Bayes plot does a few things better. So, and it was used in the original Stan workshop, so that's why I'm using that. Yeah. So what are the advantages of using Julia? It's first of all, you have a single language. So in Stan, first you have the modeling language, and then you're compiling it in OCaml, or the parser is in OCaml, and then it translates it into C++, and then you compile the C++ model, and then you typically also use that compiled model from R or Python or something. So there's a lot of moving parts. So if you're developing something new, that's pretty much a nightmare. or it's a lot of work. Another benefit is the nice syntax for defining models. So as you will see in the notebooks, the syntax for defining models in SOS and Turing is very close to the mathematical notation, and there's the original Stan code is also in the workshop, so you can compare the models to the equivalent Stan code, and you can see that the Julia code is a lot less verbose and nicer to work with. And as I mentioned before, you can use the best package for what you want to do. So if you're doing differential equations, you can use the differential equation package. And if you're doing neural networks, you can use Flux. And you can just use the full capabilities of Julia to do your models. So it's not as like it's easier to do novel things. And that's why it's nice for research and developing new methods. So why would you not want to use Julia? Is that it's like currently it's not as mature as Stan, and there's less documentation and stuff like that. So if you're using like really basic models or you're not doing anything like exotic, then you might not benefit as much. But if you're already know how to program in Julia, I think it's good times to start, because I think it has a lot of potential in the future for Bayesian statistics, because you're doing a lot of intensive calculations, and you can in Julia you can just use the one language and you get the benefits of differential equations and stuff like that. So there's, because of these reasons, or like because Julia is so syntactically flexible and it's fast, there's a lot of different packages for doing Bayesian stuff. And these are, I guess, the main ones. So SOS and Turing are close to each other. So they come from, I'd say, more of the sort of, they're more focused on sort of statistical work. And then these Janes, and Omega are a bit more sort of come from, like they're trying to do, or I don't know. It's well, I'm not that familiar with them, but they are like trying to do more exotic stuff, or like, how do I just explain it? Well, anyway, so the difference between SOS and Turing is that in SOS, the models are graphs, so you have a bit more knowledge about the structure, or like you have the full model and you can transform it, and you can do like symbolic stuff and other kinds of things. But it's somewhat limited in that it is always a graph. But there are plans to do something a bit more, but Chad knows more about that. Turing models are more expressive, because they are like, you can just use Julia inside the models, but they are also a bit more sort of not as, or they are a bit more black box than SOS, I'd say. Yeah. Okay, I guess that's pretty much it. Okay. Okay, so now we can move on to the notebooks. So did everyone get set up? Or you can ask questions if you need help getting set up. But I recommend you go at least try the first notebook in SOS to get a feel of the syntax. But then you probably want to do the, like, depending on how adventurous you're feeling, you can also use SOS for all of the notebooks. But it's I had some issues with the notebooks, so the Turing notebooks are working better at the moment. So my suggestion is that you try get a feel for both of the packages by doing the first notebooks from both, and then do the rest of them in Turing. And Tar is one of the core developers of Turing, so he knows a lot about the technical details. So if you need to ask more, then Tar is your guy. And Chad is he knows everything about SOS and measure theory. So if you need help with those, Chad will be able to help you, and I can help you with general stuff. I'm not that deeply familiar with SOS and Turing, but I know how to do Bayesian inference, like the basics. So I should be able to help you with general Bayesian inference questions. Okay, so I'll give you some time to work on the first notebook, and then we can maybe start going over them. I didn't plan going over them that carefully, but like let's see what are your opinions, or like I'm not sure how much time do you want, but maybe we'll try to get like most of the people started, and then we can start going over them. But we have plenty of time, so like just ask questions and like try the notebooks, and then we can start going over them a bit later.
Oh, what is the first notebook? Are you referring to 00 or 01?
So yeah, I guess it depends. What can we get like some kind of a poll that, or are there people doing it in sauce, or like I recommended that people do the first two notebooks or the syntax of both, so the 00 notebook, and I guess we can. There's not that much to go over in those notebooks, so maybe we'll wait until people are pretty much finished with Poisson regression, and then we can start going over. Or what do you think?
In how long is
Kusti, can you hear me?
Yep.
Okay.
I'm not sure if maybe I'm muted.
Oh, we can hear each other. How long is this going to last?
Okay, there's just a long delay. Sorry. I wanted to mention that it looks like in the sauce notebooks, okay. Sorry, my audio is very messed up. There's a big lag and it's confusing. In the sauce notebooks, it looks like there is a bug that Kusti uncovered by putting in equality immediately after the model definition. Somehow I never tried that, but if you take out the mu equals 10 and just make it 10, it works fine. So that's weird that has never come up before, but I'll fix that in the next couple of days. Sorry about that.
So that was in the first, or in the syntax notebook, or in which notebook?
Yes.
Right. Okay.
And I'll also make an update to the notebook, and we can get that in the repo with a version that works immediately. And then in the next couple of days, I'll fix that strange little bug.
Sounds good.
Because I think you're gonna just start because people. I think people are either just waiting for the setup to finish, and so they're not doing anything themselves, or there aren't many questions.
Okay.
So you could just start going through them, I think.
Sure. It's gonna take me a while to get, like, I didn't have them set up yet.
Okay, no worries.
So.
Just a heads up, I've added generated notebooks that have already been ran and executed for Turing in the repo. So there's a branch called generated, and there you find the sort of the output of the notebooks for those who can't run it themselves. Hopefully that's helpful, and I think Chad will also add similar things for SOS soon.
Tar, can you share your screen with the notebooks?
Sure. Okay, can you see this? Good.
I can see it, but I don't think. No. I think, yeah, now everyone should be seeing it.
Yeah.
I think.
Okay. Large enough. Right. You wanna get started, Christian? I'll oh, this is for the Turing model.
Yeah. If you can go over it. I'm still having some
issues.
You can go over that.
Okay. So this was not planned at all. I'm just because they is having some issues, and so I'll try to do something that resembles the beginning of the tutorial here. So yeah, so with Turing, I'll just go briefly over the syntax. And in Turing, you sort of define models using this model macro that you can see here. And in Turing, models are really just functions with some additional arguments and something that we add on the back end, which you don't have to worry about as a user. And so other than that, you can sort of, in here, you can put any arbitrary Julia code you want. And all we do is that we take the tilde statements. That is also saying that this is saying that sigma squared is sampled from an inverse gamma as a random variable. And this is just saying that it's sampled from a normal distribution and so on. And this is, standard Julia code and so on. So all these, this is sort of just a standard function where we replace the tilde statements with something that you don't have to worry about as a user. And then we just run it, and we get back, as it says there, a function once the kernel has started, of course. So wait a bit now. Takes a bit of time the first time you use it. But this was one, yeah. So you can see it returns a function, and as I said, there's nothing special about this. And then to instantiate a model, to sort of condition it on some data, we just call this function this sort of constructor. So this is demo, and what we defined was this demo function. So calling this, I get back a function, a sort of a model instance, like this, and all these details you don't really have to worry about. And then, for example, if you want to sample from the model, sample from the prior, then you just call the function like this. What this does is that it executes the body of this function, and then returns the last thing at the end of the function, as sort of a standard JuliaCon function does. And so you can see here that the ones that I passed in are now returned, even though they consider observations in the model. And so what we can do is we can change the return statements if we want to. Sometimes it's useful to return some other quantities, something that you, for example, if you compute some quantities dependent on the variables inside of a model, it might be useful to return it. And so if we run this block of code, you can see that it returns all this information instead. And we'll see later how this can be useful for inspecting the models and figuring out what's going on. And another thing that's sort of used at Turing is this notion of missing. So as I said, we can sort of condition the model on data by providing the data as arguments. But we can also consider what was originally data as a random variable if it's instead missing. So in this case, we have the same model. The y argument is here again, but instead of passing in the ones that I did before to condition on y, we just pass in missing. And once the Turing sees that this is missing, it will consider this as a random variable and sample it instead. And since we return the y here, I can make it a bit easier. I can just return y, and we'll see that it's actually different than the before. Yes, expected. And we can also do the same with the keyword argument sigma squared. Notice that I've set it here to 1, and so it's actually fixed. But if I want to sample it instead, so I can just show you this quickly, is that this, you can see that this is still 1, right? But what we can do is that we can then also set the sigma squared to missing, and then we also sample the sigma squared, which is pretty nice. In Turing, you can sort of also, because you can write arbitrary Julia code, you can also just write, for loops as per usual. The only thing that you need to sort of be aware of when doing that in Turing is that we have, if you just do this thing, which is kind of the standard, a simple way of sort of writing a for loop, where it should be like this. You sort of just define the vector that will contain the variables, and you iterate over it, and then you sample each of them. Should be an j there, right? Now this you can run, and sort of everything will be, it will work. Just return the y so we can see. Yeah, this wasn't. I remember this. This wasn't actually meant to be a model that you should run. This is just a demonstration of how you run a for loop. And the same figure, right? Because the data there hadn't been defined, so that was only for demonstration purposes, apparently. But one thing in Turing, instead of sort of the issue that happens when you write this is that this ends up being type unstable, so it will sort of become a vector any, which is not good for performance. And so what you can do is you can add this type parameter to the function, and then once you've done that, you sort of Turing will then go into your model and replace these TVs, which you see as type parameter, with the corresponding type. And this is particularly useful when you're sort of working with AD packages in Julia, which can be using different types than rather sort of the standard float 64, for example. In this particular case, if you're running forward diff, you will actually see a vector with forward diff dual rather than the standard float 64. And then it's important that you can sort of make these changes. So this is a performance consideration. And you can read more about this in like on Turing.ml. So we have this site here where you can go and check out stuff. In particular, there's the useful sections on performance tips and so on. Yeah, and you can also do broadcast the same as in Turing. So you sort of, instead of writing just tilde, this is just X sample. This is a single univariate random variable sample from normal. And instead you can do this and it will sample an entire vector if X is a vector. So this would be equivalent to this thing. But you can also, this follows the same broadcasting mechanics as regular Julia function does. And so you can also sort of create a vector on the right-hand side, broadcast over a vector u, and then sample a vector X from a vector of normals rather than from a single normal. This will be equivalent to this thing. And you can also use this alpha dot, which is just telling Julia to sort of broadcast the entire expression in her, and this will be equivalent to this thing. This sort of the dot tilde is particularly useful if you want to sort of consider like IID, independent identically distributed random variables and so on. One consideration here, which I don't think is worth going into really, but is sort of the fact that you need to allocate a variable in case you're sampling it. And so in Julia, as I said, you can sort of, in Turing, you can sort of set a variable in the arguments to be missing, and it will be considered a random variable rather than an assumption. And so if you do this, we can then check whether or not X will be an assumption, or it will be missing, and thus be considered something we should sample, right? And so if we need to sample it, we need to ensure that there's going to be a vector which can hold the variables, like hold the values that we're going to sample. Let's see a question by Matt. Yeah, so the broadcasting in Turing isn't slow necessarily. In fact, it should be faster than a for loop, for example. Internally, we still do some broadcasting to sort of computer by PDF and so on. So if it's fast to broadcast the function, then it should be fast to sort of do it in the dot tilde too. But you can use fill dist and these other functions. So fill dist is a kind of a similar thing where you give it a single distribution, a univariate distribution, for example, and you specify how many you want. And so if I sample from a rand of a fill dist of a normal 2, this is essentially the same as having a vector of length 2 and dot tilde from a normal. So a sample from this, you get 2 elements rather than 1, right? This is useful. This can be faster because it will, and if you're using reverse mode AD, this is kind of going into the weeds, I'm just going to be brief, but if you're using reverse mode AD, it's useful to work with the vectors instead, while this operator here won't have the same efficiency as broadcasting when using AD. So there might be performance consideration, but generally I find it to be pretty fast. Yeah, and so like what I'm saying here is the same thing I said above, is that really if we're doing this allocation that we're doing inside the Turing model, if we're going to do this, then we should make it a type parameter so Turing can replace it with the corresponding correct type to make things fast and so on. Yeah, and as Poisson says, that it's possible to use, for example, lazy arrays and other packages in Turing. So you can sort of, in that particular case, you could go to the above here. This one, for example, you could do something like, I think this is the syntax, something like that, where it's sort of a lazy broadcasting from lazy arrays.jl. And things will still just work and sometimes be faster. Yeah, and just to sort of simplify this check here for what is missing, I'll be writing this statement here going forward. It's quite a bit easier, more compact. Yes. Any questions about the syntax and like how Turing works and so on? This wasn't exactly planned for me to go through this, so if it's anything confusing, I have to apologize. It looks okay. Can't see anything. Is there anything on the pigeonhole? Let me check. So one person asked about, this is not sure, he asked about it quite a while ago, I think. It's Julia versus PPLs in Julia versus Pyro. Versus like in Python, for example, Pyro, which is based on PyTorch. I mean, the difference, the main difference, and the reason why I came to Julia and started looking at PPLs in Julia was because in Python, when you have a PPL in Python, you often tied to a computational framework that underlies it. For example, in PyMC3, you'll have Theano. In NumPyro or Pyro, you'll have JAX or Torch, and there's TensorFlow and so on. And this means that you have to have separate packages for each of these to be able to work with them. And you don't get this integration that you get with the rest of the Julia ecosystem. As Kirsty explained earlier, we have sort of several packages, and they just kind of work together. That becomes very, very fun when you can do stuff like put differential equations into your model. And as I said, like in Turing, you can put whatever code you want into your model, and it will run. So there's you can't really do that in the same way in these other frameworks. So in Turing, you can do everything. You can even shoot yourself in the foot. So you got to be a bit careful, but at least you can. You have the freedom to do so. That's quite nice.
Tor, I don't see this question in the YouTube or in the Pigeonhole, but it's a really common question that I hear. So maybe we should discuss it briefly. Within the Julia, so there's sort of two questions, right? There's like Julia versus Python or Stan or R, but then there's also within the Julia ecosystem, Julia is really great for developing PPLs. We tend to see a lot of them, and then there's the question of, well, how are these things actually different?
Very true.
Right, so maybe if you could say just briefly what you see as the sort of the things that characterize Turing as special about sort of its approach or that kind of thing, and then I can say briefly about SAS.
That's a great idea. Yeah, so I think with Turing, the best thing you get, I suppose, is the flexibility. As I said, you can sort of put anything inside of your model. And that means, you can do a lot of fancy stuff that isn't as easy to do elsewhere. I think that's the big thing. It is also generally quite performant when it comes to sort of static models, and you can also do dynamic models in Turing. So there's support for example, your parameter space growing, or like changing with respect to each execution and so on. So I think those are the two big things. Like essentially just encapsulated in one is, I would say, like flexibility is the big thing. But you also get a very performant model. But I would say flexibility is a big thing. Right.
Yeah, I think just being able to write arbitrary Julia code inside the function is there's definitely a big potential benefit to that, and yeah, that's something that I guess there's also Gen that has that kind of flavor, and maybe maybe it would be too far a diversion at this point to talk about the details of the distinctions between Turing and Gen, but that's also another excellent PPL to look into. As far as SAS, I think the thing that I see as sort of characterizing the package and making it stand out in the ecosystem is this idea that in SAS, when we say @model, SAS actually just captures that the code that you enter below that, and so in what we currently have, we currently focus on the restricted case where you have a DAG, where you have just a collection of top-level statements, each of which is either a tilde or an equals, and you can still do complex nodes. For example, we have a for combinator instead of a for loop, you would use the for combinator. And so that makes it very easy to build these more complex distributions within a model. But the internal representation being in terms of expressions and then doing runtime code generation gives you a lot of power. So in principle, a sauce primitive can generate just whatever code you want. So you can, it can be very powerful in terms of going from that expression, whatever input type you call it on, and then generating specialized code for performance or different kind of inference methods.
So the reason why I got interested in SAS is because I'm working on like approximate Bayesian computation. So there you don't have like an analytical likelihood function, but you have a simulator that you put inside the model. And I feel that SAS is more like it's easier to like use it as a sort of like probabilistic glue. So you can just like use external packages, but like or like it's not in the same way as Turing, or that's the feeling that I get.
It's maybe worth mentioning also that I know that Turing had a very strong goal of getting to a point of stability with the language, and it's also more mature. Literally, it's an older. It's not in the sense of old, but it's been around longer and it's had more time to mature. The community is much bigger. There's a larger team working on Turing. SAS, by comparison, has a little bit more of a let's say experimental feel, but there's definitely a lot of it that's still in the growth stages. The upside of that is if you're interested in getting features into one of these PPLs, or if you're interested in contributing to one of these PPLs, I think we're still in sort of rapid growth phase in SAS and also in measure theory. So very excited to get community involvement, community contributions to these things. That's my sales pitch.
So it seems that my computer is completely broken now. So even my like I can't even pull from the Git repo. So like my SSH is timing out. So I can explain the static notebooks, but it's like I'm pretty crippled. But it's really unfortunate. But should we go over, like you discussed a bit about the differences between SAS and Turing, so maybe we could go over like the syntax for SAS and then go into the models.
Sounds like a plan. Do you want to do that, Chad? Because I mean,
yeah. If can we just stick with your screen, because I feel like we don't need any more technical hiccups.
Yes, but I am uncertain if they're runnable. I haven't tried them.
Yeah, that's okay. We'll.
You want to take over, or do you want me to try them?
You know, I think you're closer to having it ready than I am at this point.
Okay. Okay.
I don't want there to be more delays.
Yeah, I'll give it a go. Let's see. Oh, and also I saw some questions about something about people seeing variables being undefined. Some of these blocks are not meant to be executed, just for the record. Like, for example, this block this is how you use it inside of a model. It shouldn't be executed outside of a model, just for the record. But yes. Okay. Cool. Let me see.
Yeah, so I can maybe talk through these things a little bit as you're running them.
Exactly.
If maybe let's go to two things. So measure theory is a package that attempts to address some of what I saw as issues with distributions.jl. It also uses distributions internally for sort of a fallback for some cases. And also SAS you can use with measure theory, but you can also use SAS just fine with distributions. So there's some flexibility in that sense. This normal to the 10th power, think of that like if you say R10, you know, R to the 10, then you get, that's exactly it. It's a product. It's a product distribution or a product measure.
So it'd be equivalent to this and
it's basically that.
Or this. This is essentially the same as this.
Yes.
All these deployments.
Yeah, so field is in Turing and the product is in SAS or like measure theory.
Exactly.
Yeah.
But
and
field is Just like
Go
fill
ahead.
this is in distributions ad.jl. So it's a separate package for Turing from Turing. It's just that we use that package in Turing for AD compatibility with distributions.jl.
Yeah.
Yes.
And this is another nice thing about the Julia ecosystem is, for example, I can use distributions AD within sauce. So there's nothing sort of so Turing specific. And in fact, I've connected to a few other packages that are developed by the Turing team. So the Turing team, I think, has been really great about making their packages more general use and not tied specifically to Turing the language. So there's a great kind of community vibe about all of it. So in this, well, this is a little bit, there's a couple bugs here. So the tau should have a square root.
All of them?
No, or you can do that. Yeah, and then make that a sigma squared. And I think that should work. Maybe if you make it, might need to be in a prox.
This should be correct because the sigma is squared under the, like, tau is like 1 over sigma squared.
Yes.
No, but
Yep.
So this is
So,
good.
yeah, make it in a prox instead of equals equals.
Oh,
So
wait. This is some old version. Oh, crap. But yeah, okay.
yeah, try that. So in what? Oh, nope, this is wrong. Okay, so add one more line that says above that, just under the tau equals, that says something like x equals rand normal mu sigma squared. Sorry, these
Yeah, it's
and
like
the
this
log
is
density
not
needs to have a
related.
comma x.
Yeah, that makes sense. That makes sense.
Okay. Make it a sigma and make tau a square root. Okay, yeah. So so here you see the new growth in packages, and
I mean, like this. What do you want?
yes, no, just make it a sigma. Make it a sigma and then make tau square root of sigma. Yeah,
Oh, square root of sigma.
yeah. Okay, yeah. So
Yeah.
yep. What?
Should it be sigma squared?
It was like, I think it was like you have sigma and then you have tau is 1 over sigma squared. That should be correct. That's just mu is 5, sigma is 10, and then tau is 1 over sigma squared. So add the squared.
That's squared, not square root. That's right.
Yeah.
Right.
Oh yeah,
It should be
yeah.
sigma squared, right?
Yeah.
Yeah. That's
There you go.
why. That's why.
So,
That's
yeah.
why I asked.
Yeah. So I want to mention that this is a nice thing about measured theory is that we allow different parameterizations. So instead of just saying there are two numbers and there's nothing special about them, in measured theory we actually track here are the names associated with each of the parameters, and then we can do things like this. We need a RAND method apparently for the sigma squared parameterization.
Let's get next block.
Yeah, and here there was a bug with mu equals 10. So move the mu into the arguments before the begin. This is a bug I should have fixed in the next couple of days, I'm sure. It's
You mean like this?
yeah, that's fine. Or just mu. Yep.
Yeah.
Yeah. Yeah, so this is a little bit different than Turing in that think of this like a function. So it just takes, here we take a mu as an argument, and the thing it returns is a distribution over x. Yeah, and then that needs to be mu comma sigma in the arguments in the next one. Yeah. Yep. And then make it mu equals something, sigma equals something.
So it doesn't matter.
Yeah, it shouldn't matter. Yeah. So, and this is another thing. These are named tuples, but we don't really care about the order. So if we say mu sigma in one place, we can say sigma mu in another place because it's the names. It's using the names for dispatch and not the order of the arguments.
Can I have a question?
Of course.
Is that like this also? I forget. Is nested modeling a thing?
Nested modeling is a thing. Yes. So you can have a model within a model.
Nice. And like, how will it then capture all these arguments?
The arguments.
Will this get recurse into the nested models? I guess is what I'm asking.
Yes. Yes. You use a nested named tuples.
Nice. Cool. You want to go on next?
Sure. Yeah, and my model too. It's just a measure or a distribution. I mean, literally, it's a measure. So in measure theory, it maps to a measure. So if you add a mu on there, then this should work. In the next one down.
Oh, yeah.
There you go. Yeah, and this should give you a sample. And then for observations, yeah, so give you a named tuple as a sample. And for observations, this is the usual kind of mathematical model or a distribution conditioned on something. So the thing you condition on in this case is the named tuple. And as you mentioned, Tori, this can be a you can have nesting here. And there's no mu, so you would need a mu there, but it doesn't matter because we're not going to do anything with it anyway. Yep, and so here's another one with just an IID model. So this, instead of saying normal to the 10th power, we have this notation where you can call an IID combinator on anything. So this is take a normal distribution and pipe that into IID of 10, which then turns it into something that builds a joint distribution. As I mentioned with for loops, instead of having a Julia standard for loop, it works out a little bit better in Sauce to have that using this combinator. So we have this capital F for combinator that uses Julia's do notation. And so this is, there are a few different ways that you can use this. Here's an example of one where you just say the indices are going to go from 1 to 10. And for each index, we're going to build a normal with mean I and standard deviation I squared.
Yeah, so this is kind of like, similarly as you said, like in Turing, this would be different. There would be like an actual for loop, or you would use an array dist. You can also essentially like a fill dist, but you can do it over where each element can change rather than having a fixed element. This is like this looks much nicer. Yeah. Should I go further down, Christy?
Yeah. Well, wait.
No.
Yeah. Is this okay? It seems that I forgot to push the latest version or something because I had originally fixed those previous ones, but I'm wondering if this is still.
Maybe one more thing to mention here is that this. So we have a RAND method, but then because Sauce works in terms of source code generation, you can also say, give me the source code that you would generate for a given primitive. So when you call RAND, this is what Sauce literally does: is it generates this source code, and then it there you go. It generates this source code, and then it does runtime code generation and compiles it at runtime. So it doesn't use eval, but you can sort of fake it what it's doing and use eval like this and confirm that it's the same thing. So yeah, that's a nice example, Tor.
Yeah.
So I wanted to say something about the posterior predictive function. Like go up there. Yeah. So this is just a demonstration of this predictive function or in Sauce that you can use to transform the model so that it's you can basically get the data generating function. So if you have samples from the posterior, then you can use the predictive function to transform your model so that you can generate like predictive samples. And then I've implemented it elsewhere, but this is like an exercise, so you can figure out how it works.
I think actually this was like cool, maybe a bit complex, but this is a nice demonstration, I guess, of what the difference between SOS and Turing is. That SOS will do source transformations, right? So, like you generate the actual code, while Turing kind of pushes that onto the Julia compiler. So we use a lot of type information and so on to give the Julia compiler as much information as possible for it to just compile things away, while SOS makes sort of active, it sort of works on the code itself and generates expression that then turns into like runtime generated functions. Is that correct?
That's correct. And of course, the runtime generated code will still go through the same Julia compilation. So it's the different. Let's see. Yeah, I mean, I guess it adds a few more. Yeah, so maybe it's like it adds a few more capabilities for manipulating the code at the syntax level. The trade-off of that is, in order for there to be much benefit to that, you need a little bit more structure in the code. So that's exactly. Why SOS tends to be a little bit more restrictive, so that it can reason about things statically.
Yeah, while Turing will probably run, but it might sort of in the cases where SOS might not work, Turing will still run, but it might like give you bad performance, for example. It's kind of like, I suppose it's kind of like that. Cool. All right. So that's the syntax.
Okay. Yep. Let's go into the models. I guess everyone has had plenty of time to work on them.
Yeah. Well, you wanna go out? Want me to open it?
Yeah.
Okay.
Let's let's go Turing. Let's go with Turing. But they're essentially the same.
Should I run the solutions, or I guess I should, because otherwise I won't be able to see the results. By the way, I saw some people complaining about text size. I tried zooming in a bit more. Is this better? It's quite big. Hopefully this helps. Yeah, you want to take it away?
Okay, so I guess you already read about the problem, but basically we have cockroaches in apartments, and we want to determine the optimal number of traps, and the traps have a cost associated with them, and so we want to minimize the cost of the setting the traps costs something, but also getting complaints from the apartment dwellers about cockroaches, that has a cost associated with it as well. So we want to find the optimal number of traps that for to maximize the profit. Yeah, I guess that's enough explanation for the problem. There's a formal model as well, but that's basically what I said.
Sounds good. Yeah.
Yep.
This is sort of the data that we have available. This is the number of complaints per building, which is kind of the things we sometimes want to use as observations, because we want to minimize the number of complaints, right?
Or it's a bit, or basically we want to model the number of complaints given the properties of the apartment and the number with respect to the number of traps. So there's you can see in the formal model, there's the lost revenue is R, and that's a function of the number of complaints, and that's a function of the number of traps.
Yeah.
And then there's the total costs of setting the traps, which is TC, and then we want to find the argmax, so the number of traps that basically like optimize the total profit, or like the expected total profit. And now we're going to model the number of complaints, and we're starting with Poisson regression because that's the basic model that you start when you're modeling counts.
Yeah. And so the test data has been loaded in this setup.jl that we ran at the beginning. So we can run this to get the number of buildings, and then there's some plot set which are insanely small for some reason. I don't know why.
Yeah, so this is like the exploratory data analysis phase. So you can just get a feel for the data and like see what would be useful for determining predicting the number of complaints given the regressors and the number of traps and so on.
So there seems to be like something weird going on here with the theme. But on the x-axis, you have the number of traps, and then the y-axis, you have the number of complaints as a result of the number of traps. So you can see like the ones that have fewer traps, have higher, more complaints.
Yeah,
which makes sense. So what is live in super, Christy?
So that's if there's a superintendent living in the apartment, so someone takes care of things.
Yes. Or discover things, or be affected by themselves. Here's the date, and there's data and access and the number of complaints on the y-axis. See it increases over time. Curious. And here we can see how often. So you see a histogram of the complaints, sort of how many times you get 5 complaints and how many times you've seen 9 complaints and so on. You just shouldn't see whenever you want to tell them. And here we can also see this thing that we do see like there seems to be a relationship between not being a superintendent living in the building and the number of complaints that we're seeing and the number of traps that we're setting.
Okay, and is there some? Yeah. So we went over the Bayesian workflow in the beginning, and now we start with well, in this notebook we don't actually have the prior predictive checking, but we start by just simulating the data. So we encode this Poisson regression model. Let's see if you can scroll down to the Poisson regression. Yeah. So we model the number of complaints. We say that the number of complaints in a certain building in a certain month is distributed as a Poisson, and with the parameter lambda, and then we have this linear term here that's goes through this exponent, and then that's the lambda term or the lambda parameter. So that's if you've ever done Poisson regression, this is just the basic Poisson regression.
Yeah. So like log linear model on this lambda, and that's the mean for the Poisson at every building and every time. Do we consider time at the beginning? I don't think, do we?
Well, it's the data is like in
sequential.
So, yeah.
Yeah. Okay. Yeah. And so here's the corresponding model to this thing here, where we're using a particular prior on the beta and the alpha, which are described here. As I mentioned, sort of the thing that I showed in the syntax is that we have traps we don't want to do anything with. This is kind of the input, so what we condition on. And then we have complaints, which are the data that we sort of like. This is sort of the data that we want to model because we want to take an expectation, as I said before, over the complaints. And as I said in the syntax, you sort of in Turing, what you can do here is that this is a function which provides keyword arguments. And then we give it the traps, and these need to be specified, and the complaints can be optionally specified. If they're not specified, they will be considered random variables because they're missing. If they are specified, they will be observed. And so this is the same thing as I said before, where you have if they're missing and they're going to be sampled, we need to allocate something where we can put the results. And as I also briefly mentioned, so the nice thing about Julia is awesome. And so because you have the type information here, it will sort of it will compile this branch, this if statement away, meaning that if you set it to missing, then you'll see this branch, then this branch will actually be executed. But if you set it to something else, this branch will never sort of be seen or executed, be compiled away. Then we use this dot operator that I mentioned, where this will sort of mean that what this actually means is that because traps is a vector of reals, we will sort of, it's the same as putting a dot in every one of these, meaning that on the right-hand side here, we end up with a vector of Poisson distributions parameterized by these here. And then we do the dot tilde. Also just return the random variables, so that because it's nice to look at, a little bit nice to sort of for visualization purposes and so on afterwards. Run the model, we get this back here, and then we can try the model out. We'll do that here, but below here. So we generate some fake data, and then we sort of I guess this should be, yeah, and then we give it the fake traps that we just generated, and then we can call the fake model, and we give us a fake return value as we saw here, this alpha and complaints, and run this, we can see the result there. First time it runs, it just takes a bit because everything is compiling and so on, and then afterwards it's really fast. As you see here, there's the alpha. This is a sample from the prior, and since we haven't specified the complaints, they're missing. We get a sample from the complaints too, which is sort of something we'll observe on later. And so a nice way to sort of assess the parameter, like the model, is to sort of make sure that we code everything correct. Is to sort of condition the model on these fake or for sort of data that we just generated. And so what we do is we call the sample function. We take the model instance that we condition on the complaints now. So now the complaints are specified, and we're going to run nuts on it, and we're going to run 1,000 samples, and we plot them afterwards to sort of get an idea of how the sample, how the stereo looks. Yeah, so this is like it take a bit at the beginning because it will sort of compile the model and compile its gradients and so on, and then once that's done, it will be fairly fast. And afterwards, we look at the posterior predicted distribution for the posterior that we generated, and this means that we're going to take the model and then we're going to remove the observations that we just observed on, because now we want to try to predict them. We want to generate them, and so we want to treat them as random variables. So it's sort of, I could also write it like this. And in SOS, it would be the something like this. Oh, I'm not missing. It would be like, oh yeah, it would just be like this, I suppose. Not conditioning or anything.
Yeah, so you can see that the posterior samples are in the histograms in blue, and the parameters that we use to generate the fake data is in the black lines here. And this is useful for testing that your implementation of the statistical model is working correctly. So this was really useful for me, for example, when I was testing out measure theory, and like there was and like adding new parameterizations for like log linear Poisson regression, and then we caught a bug with Chad. So this is useful for making sure that it's actually doing what you want to do.
Yes. Yeah, someone asked if I'm using RVis.jl. No, we will be using it later, but this is actually using I think baseplot under the hood.
Yeah.
So this is our package.
So in the future, it would be nicer to have this in Julia, but for the lack of time, I just used the base plot. So it's Arbis is I couldn't. I'm not that familiar with Arbis, but it didn't have all of the, or base plot seems to have more PPC plots.
Yeah, you can do all this in Julia. I've added some Arbis plots later, but it's but even Arbis is using Python on the hood, right? But you can actually do all this also in just using stats plots and so on. But you need to code a bit more yourself.
Yeah.
What about the autocorrelations in the count data? Is there a consideration for that here? Not yet. There will look more into sort of how. I mean, they won't actually. There's a very late tutorial. We're not going to be able to go through it, but there is one where we sort of count for correlation through time in the count data. But we're not going to do that now. No.
Was the question about the autocorrelations from the sampler?
No. Chain? For the in the count data, yeah.
Okay, right. So yeah. So the time series that we did, I dropped it out of the workshop because I didn't have I didn't think there would be enough time to cover them, and I didn't have time to implement them properly. So they will be added later, but they're not there yet.
Yeah. When do we need to? How much time do we have actually?
We still have 1 hour and 20 minutes. So maybe.
Yeah, you want to keep going?
Yeah, I guess so. Like
just making sure, we're not running out of time or something like that. So yeah, so we'll. Okay, so the next thing we'll do is we'll look at the posterior, like the predictive, the posterior predictive, which is sort of the distribution of the complaints under the sort of posterior that we found on the parameters, right? So we obtain samples for alpha and beta, which specifies the entire model except the complaints. But the complaints were specified by the data before. And now we say, well, we're going to drop the complaints and we also make these random. But we're conditioning on fake posts. Fake posts is the chain we just generated. And these fake traps. And so now we're going to fix alpha, beta, and the traps. And then we're going to generate the complaints. Right? So this is kind of what it's saying. Posterior predictive is using Turing.predict under the hood. It's just sort of converting it into a name tuple afterwards because that's more consistent with tutorials for SOS and so on. So it can make it a bit more consistent across the DBLs. So if we run this, we will sort of get what's this is sort of predicting on the in data traps set. So we'll get a like representation here. Here we have them, a bunch of named tuples, all with complaints, you see. So these are different samples of complaints. And then we can plot them. Yeah. As you can see, it does a decent job of fitting the data. You want to add anything here for this plot?
Yeah, so this is the posterior predictive check. So I guess there's not that much to cover. So basically, you want to. So this is this the fake data or?
Yeah.
Yeah. So you can see that the actual observations are in the backline, and the samples from the posterior predictive distributions are in blue, and you can see that it's not surprisingly fitting pretty well because it's using the fake data. But we'll see more realistic examples of this plot when we go into the real data.
Exactly. But this at least verifies that likely we'd coded things up correctly. Yeah. And there's nothing wrong with the samples going on or anything like that. And yeah, there's also this rivergram that you can plot. You want to say anything about the rivergram, Kristi?
Well, it's basically saying the same thing, that we're the observed number of counts are fitted pretty well to the expected number. So it's it says the same thing as the previous plot, but looks a bit different.
Nice. Yeah, and so now we're going to actually use the real data rather than the fake data. So we go through this process again of creating this model that we instantiate on the best data traps and the best data complaints, sample nuts using nuts, and then we have 1,000 samples. We'll run this. As you can see now, now it just finishes like that, 0 seconds instantly. The only thing I'm waiting for now is the show method of the chain, because it takes a bit the first time you also run that. And then we can also run plot the posterior afterwards to see. So here you can see this is the output of the MCMC chains. Here we can see the mean of the parameters of the alpha and beta, standard deviation. We get the ESS, which is the effective sample size, which kind of means so we ran it for 1,000 iterations, but the effective sample size is 230, which means that there's some autocorrelation between the samples, and so the independent samples effectively that we get there are only 230 of them out of those 1,000 iterations. I mean, they're essentially the autocorrelation is probably vanishing after every 4th iteration. So you can if we thin this by 4, we'd probably get the pretty much we get 250 samples left, and then we probably have an ESS that's similar.
Yeah, there was a question about the rotogram plot, about what it means, but I'm not entirely sure what the shaded area means. So the easiest way to find that is to look at the base plot documentation. So I'll post a link to that.
I'm guessing this is the mean counts, right, for each sample?
Yeah, that would make sense.
So this is kind of just the this would just be sort of the I guess the some HPDI around the sort of the high density the region. So this will sort of cover essentially
that would make sense.
95% of the sample values, probably. That's what I would expect.
Yeah.
Do you know the value, Gaussian? No.
Not yet.
Okay, we can maybe look that up afterwards. But yeah, we can also plot it using stats plots. For some reason, this plot is very small. I don't know why. This doesn't happen when you don't run it in a notebook. I just noticed it now. So this is kind of strange. What if I do? Let me see. Interesting. Okay, cool stuff. Yeah, so I guess here you can see the plot. So as you can see, this is how you can see the density estimate of the posterior distribution over the beta and the alpha values. Yeah, and so do you have any comments, Kirsty?
Not really.
Okay, move on. So now that we sort of have a posterior, we have a chain that's conditioned on the data, a sample on a model that's conditioned on the data. We now want to try to actually generate and predict the number of complaints, sort of to see how closely the fit then fits these. How closely we can reproduce the observed data using the parameters that we found for the model when conditioned on the data. So it's just making sure that we can properly sort of reproduce the observed data in the model. Because if we can't, that means that there's the model is probably wrong. So we can run this, get a bunch of samples, and then we can plot them. Here we can see a bunch of you can see all these sort of the density of these y's that we generated. So here we can see all the values that we sort of generated, and there's essentially like a kernel density estimate to the histogram of the values.
And we can see that we're not the number of zeros is not we're not fitting that all that well.
Yeah,
so there's a lot of zeros in the data, but we're not fitting it well.
Yeah. So essentially like the sort of distribution is distribution of the model conditioned on the parameters, given that it's already seen the data, it's still shifted towards the right versus the true observations. And so that, it gives an indication immediately that there's something wrong here because we're already conditioned on data. And so, I mean, there's still quite a lot of information encoded in prior, so we need data to sort of shift the prior towards the posterior. But as we can see here, it's quite a bit further away than we expect. And as Christy said, in particular for values close to 0, there's an issue.
And here we're using the number of the proportion of zeros in the data. So this makes the issue a lot clearer. So
exactly.
The actual number of zeros is like 0.2. So like 1/5 of the data is zeros, but we have in our model we have a lot less, quite more. What did I say?
Yeah. So the black line here is
right.
the sort of the as we can see, 20% of the actual observations are 0, while under the model, under the posterior predictive, we see that there's quite a bit fewer. We see there's not few zeros than there is in the actual data set. And so we can see that clearly the model isn't the prior that we made, and the sort of the model that we set up does not put enough probability mass on values close to 0. So this we just already explained, and then we can also plot the QQ plot again, super small for some reason. So we'll go to the alternative. As you can see here, so what you sort of would expect is that if the values align properly, you would see all the dots along the line here. But instead, you have this thing where the values are higher in the data set than we have on the line there. Right? This is for the wrap here. Yeah. Do you want to explain something about this, Steve?
No, I don't have anything to add.
Okay. Cool. Yeah, and we can again plot this plot and see that the counts are, so the observations are essentially the model is underestimating the observations. So. Yeah.
So like basically what these plots are saying is that just a simple Poisson regression is not the best model to model this data. And now we can start exploring more complicated or like more or different models. And the next model is like we're adding new regressors. So in this model, we only have one term in the linear or in the log linear. What did you have? We have like a
log linear
intercept, and we have the like coefficient for or the slope basically. Yeah.
So here we only have like the intercept and then the beta, which is the and then we can plot this sort of brief interval plot, and begin what we can find. And here you can see there's a number of traps along the x-axis and a number of complaints along the y-axis, and we can see how poorly the posterior predictive actually fits the observed counts, and particularly for the lower number of traps. So if there are fewer traps, the number of complaints is not fitted well. And there's also some cases, for example, for these larger ones. All in all, as Christy said, it's telling us that the Poisson, a simple like log linear Poisson, is not sufficient to be able to say anything, to be able to model this problem. In particular, like the tails of it. And yeah, as I mentioned, that we'll be using some Arvis, and this is a rather big function that sort of essentially what it does is it takes in a prior model, which is the one with without the observations conditioned, and then the conditioned model, which has taken in the data, and then posterior samples, which is a chain that we've gotten from sampling this conditioned model. And then we just run through all these things, and we sample the prior, we sample the prior predictive, we sample posterior predictive, compute the log likelihoods. This is all just running it in Turing, and then we eventually just convert it into something that Arvis can use, because Arvis.jl is a very useful visualization package. So this is actually included in the sort of the setup.jl, but I added here for sort of demonstration purposes, where you can see how to sort of sample from the prior and how you can predict in a model. So I can quantify its log likelihoods. But with this, we can get a lot of we can investigate the posterior further quite easily. So run this and convert it to Arvis. Takes a bit because again, it's the first time I'm running all these things. And then once that's done, we can plot. We can, for example, plot the. So now that's done, we can see this. This is the output. The inference data here is the output, and we can. It's pretty nice. You can expect them like this in the Jupyter notebook and look at them by opening up the chains and see what the coordinates have and so on. And yeah, and we can then, for example, plot this comparison, and this comparison is comparing the prior to the posterior. So here we only have a couple of variables. We just plot them for all of them. So here you can see the prior of alpha and posterior of alpha, and here they all sort of put out on top of each other. As you can see, the data has clearly informed the distribution quite a bit. We moved the density has all moved quite a bit to the right. And the same for beta. And so you can see that it's not so probably it wouldn't help to just change the prior parameters on beta very much. It seems like there's more because clearly the data has actually informed the model. So it's probably more a issue of how simple the model is rather than the parameters, the hyperparameters that we chose for the prior. Right? So if we go back to the model, it's probably not going to make much of a difference. I change this to a 5, for example. Because as we can see, the prior doesn't make much of a difference after having seen so many observations in this particular case. As we can see here, it's changed quite a bit. And yeah, this is essentially the same plot as above, effectively. Just a different approach to it. And yeah, so this is the first sort of tutorial. Right? It sort of gets you up and running and shows you why it's not sufficient to have a simple exponential model for this problem. Yeah, should we take like a 5-minute break?
Yeah.
And then move on to the second one if we have time?
Yeah, I mean, there's maybe we should at least cover the sampler diagnostics. But other than that, I think the second Poisson model is basically the same. It's just a slightly different model. But let's see. We can probably just cover the model syntax. It's other than that, but let's maybe we can take a break.
Yeah. Those Matt asked if I can use the VAC, and yes, you can. So always provides VAC. It also provides the LU, which is the sort of the LU fit, which is the approximation to sort of leave one out, and it's not working for some reason. Blue works, okay. So there's a bunch of statistics, a bunch of metrics that we can then sort of use from Arvis.jl, which is pretty nice. That's like thanks to Safax and then a bunch of people that sort of implement all these things. He does Julia side, and there's a bunch of people that have done like nice stuff on the Python side. Cool. Can't see any more questions. Someone asked about a Julia Lab environment. I don't know. Probably might be useful. Maybe that would be a good idea. Someone asked if the Jupyter is displayed in the Jupyter notebook. Something like squaring is displayed as a superscript of 2, and other times it's displayed as a square like soup to like an upper arrow to. What's causing the difference? This is just someone in the chat answered. Nice. This just allows Julia allows unique variables, and that's kind of the answer. Someone asking about Bitcoin. So regarding Bitcoin, I don't want to give advice. Sorry. Yeah, I think that's all questions that are there right now. Should we maybe take a break then?
Yeah, let's take
5-minute break.
Yep, 5 minutes.
Sounds good. All right.
So we'll be back. Well, depending on your time zone, but 5 minutes from now.
Yeah, 5 minutes. Usually 5 minutes is the same in every time zone.
Yeah, that's true.
Usually, depending on the gravitational field. But yeah, see you in a bit. Well, I am back. I figured I'd mention for everyone who's watching this and thinking, man, this guy seems unprepared. It's because I am. This was not the intention that I was going to be presenting this because of all the technical issues.
Yeah.
This is how it is. But yeah, I'm reading this for the first time with you people, so we're learning something. together.
Yeah, this definitely wasn't supposed to go this way, but yeah.
Such is life.
Basically, I was in March. I was like, yeah, I'm gonna do this workshop, and then like I wasn't planning on moving to a different country, and like took way more time than I expected, and then I just didn't prepare properly.
Plus, you moved from you moved down the ladder. You moved from Norway to Finland. I mean, that's a great.
Yeah,
that's a bad choice. That's a bad choice.
No. I like it better here.
I do envy your snow.
Yeah,
if there is any. But yeah, go on.
Yep.
Got some caffeine. All right. So what we're going to do now is we're going to add more parameters, essentially. As we said before, we had this simple model. It's just the alpha and the beta, and sort of multiplied by the traps. So we have like a simple log linear model. And we're still going to have a simple log linear model, but now we're going to add the log square foot. And the reason for this is if we plot them, so here we're sort of using ggplot, and we're plotting the number of complaints. Also using data frames there to sort of convert the data frame into something that we can work with. This I learned this week in watching a tutorial on data frames. So this is pretty nice stuff. But so what we're doing here is we're converting it, the complaints and the total square foot to be on the log scale, and then we're just plotting it to see whether or not there's a relationship between them. As you can see, there seems to be a relation between like the number of complaints increasing with the sort of this total square footage of the place, and so that means that it might be a good idea to add this additional factor for each of the buildings. This is index for the buildings. The traps are buildings and time, and then we have these two other things. So this adds another number of buildings parameters, which I think was 10, to the model. So what we do is we transform data, press data that were originally loaded, and I will add in this using data frame's nice syntax, or we add in the total square foot field, which is the total square foot. We add in log square foot, which is the total square foot divided by 1,000 and the log of it. And this is the resulting data frame. And then again, we implement this model. There's in the original notebooks is going to be this is going to have some missing pieces, and you're sort of encouraged to implement them yourselves if you really want to. So I have seen a question here.
Yeah, someone's I didn't like. Oh wait.
Yeah. Okay. Maybe you can.
Yeah.
Deal with the questions then.
Yeah.
Yeah. So as we see how we add, we also add in this live in super, which is whether an indicator whether or not the superintendent lives there. As we said earlier, they seem to have some relationship between with the number of traps actually being placed and the number of complaints. And so we added also beta for this super. And on top of this, we have this log square foot that we're adding as like a constant to the entire model. So there's no coefficient on this thing, but we do have the live in super coefficient. And again, we do this complaints thing, the missing part. And this is now it's just sort of a bit more compact than we had before. As I said, this will be compiled away by Julia's compiler, which is pretty nice. So if I run this model, instantiate it, generate some fake observations once again, so we get some notion of whether or not the model works. So as we see here, we can sort of just sample some Bernoulli variables because these are indicator variables, and then some of these we have like a log normal here on the square footage. And here we just instantiate the model and then run it again, and then we get back some fake data. Remember, because as I said, we get the return statement set. We get back some fake data. Fake data is nice. And then we want to make sure to ensure that everything is correct and the samplers are implemented correctly and so on. We might want to then do this to sort of sample from this from the multiple Poisson regression conditioned on the fake data to ensure that we can recover the parameters. Do this thing. Everything is nice. I'm trying to go through this rather quickly because it's not such an interesting tutorial. The next one's probably more interesting. And we can then post the recovered histogram. As we can see, it's still not doing a pretty good job. It's still doing, well, still doing a pretty poor job, to be honest. So as you can see, the black bar here is the true parameters, and then there we can see the sort of the estimated ones is the histogram here. And as you can see, both alpha and beta are not really covering the true parameter very well. The beta super is covered pretty well. And I'll just to remind you that we have access to true parameter because we did simulate it and then condition the data on it, because this is all fake data. We haven't even got to the real data yet. So now we'll do that. We will now, instead of condition on the fake data, we'll condition on the true constraints, the real constraints. We do exactly the same as we did before. Sample. We get the result pretty quickly this time, and then we can also generate posterior predictive. I'm gonna conditioning on the posterior samples that we just got. We generate samples from the posterior predictive. We plot the density here again to see how it looks. And again, we can sort of plot this proportion of zeros to see whether or not we've done a better job of capturing that. Because remember before the last tutorial also. So actually here you can see that indeed the posterior distribution has now shifted to the left, right? The last time it was more moved to the right with the peak. And so this seems to do a better job of reflecting the true the true observations, and the true underlying generated distribution. But it's still clearly not, it's still sort of not putting enough probability massing on counts near zero. And it's also not putting enough probability mass on the tails there. This is the same thing as we saw on the previous tutorials. It's still, even after adding sort of additional parameters to this model, it seems that it's not sufficient. And then here we see the same thing. Shift to the right seems to do a better job of capturing the zeros, but still not enough. We can plot the PPC intervals. As you can see, it's getting closer, it's getting better, but still not enough. And here it's pretty good now. So yeah, essentially the extreme events, but on either side, be like close to zeros or higher values, are not really captured well by these two models. Which brings us to the negative binomial model, which is indeed an attempt at fixing and addressing this issue.
Right. So I'm gonna butt in here. So in Poisson, the Poisson distribution, the mean and the variance is the same. So that's lambda for both of them. So if the variance of the data is not the same as the mean, then the Poisson will just not work for the data. So that's why we're using a negative binomial, which has separate parameters or it has two parameters. It has one for the mean and one for this overdispersion, which is like this, so like this dispersion parameter, basically. But it, So we're using. So now, so that's we're using negative binomial to just because it's likely that it will fit the data better.
Yeah, it gives you essentially more freedom. There's also an interesting relationship between negative binomial and Poisson, whereas I think negative binomial can still be viewed as a mixture of Poissons, I think, or something like that. I'm trying to remember. Yeah,
or here's in this parameterization, if you so if you look at the variance here, variance of the data, you see that if you let's see. This term, like lambda squared over phi, approaches zero when this phi gets large. So then it approaches a Poisson distribution.
Yeah, I guess there's more of the definition missing, right? You don't have more than just two non-zero moments, right? But I'll take this as truth. Yeah. So exactly. The point here is that negative binomial allows you to sort of put more, gives you more flexibility what you can do. What you can express with them. So we're going to use this as the likelihood rather than Poisson distribution. Again, yeah. So what we'll do here is that we have this negative binomial 2, because the negative binomial from distributions of JL is parameterized differently than what we want. We want parameterized by the mu and the phi, and this is the relationship between them, between the parameters in the negative binomial in distributions of JL and the negative binomial that we want. And so we just make a sort of convenient constructor for this thing. Then we will sort of reuse this inside of the model.
And in measure theory, this is a lot more convenient because there's already a few different parameterizations, and then you can just use the same name or the same constructor, or you can use the negative binomial constructor, but you use keyword arguments that are named differently. So if you want this parameterization that uses mu and phi, then you can just use mu and phi as the keyword arguments, and then it will use this different parameterization.
Yes. I think that needs to be the... Yeah, so this is the model definition. Nothing too different. We say these parameters are reused from before, because again we have this sort of this effectively log normal model on the mean, but now we have this phi here, and this so just convenient to parameterize it using the inverse of inverse of phi rather than phi itself, and then we provide it as a second argument to negative binomial 2. So other than that, there's nothing particularly interesting about it, more than now with that we're using negative binomial 2 rather than a Poisson with this additional parameter. So there's just one more parameter. We'll see if this helps us in any way to do what we want. We're hoping that this will then help us capture the tails of the distributions better. So again, we do this process where we generate some fake data, and then we condition on it, and we run sampling on this conditioned fake data, and then hopefully we recover the true parameters, just to be sure that samplers and the distributions we implemented are working correctly. So while we wait for that, next thing we do, it's the same as we did before, but now we're just conditioning on the test data, i.e. the observations, rather than the fake data we generated. Again, using nuts, using 1,000 samples. So nothing particularly changes.
Yeah, let's speed up a bit. I want to get to the
default one. Cool. Yep. So then we can also generate the area, plot, same as before. Again, we plot the proportions, and now we'll see that things are looking much, much brighter. I did run this, right? Oh, I forgot to run this. As you can see, there's quite a bit of numerical errors, which is unfortunate. We'll get to that in the next tutorial. But this is an indication. Like when people see this, is quite a lot of people are quite worried that there's something wrong happening, and yeah, it kind of is. But this isn't necessarily saying that the sampler has broken. It's just saying that as the agency, since we're using, as you can see, it's using the advanced agency in this particular case. It's just warning us that there are numerical errors, and so there will be sort of gives you an indication that likely the geometry of the space that is sampling from, the geometry of the density is potentially sort of ill-conditioned in the sense that it can it's not a smooth, nice Gaussian, for example. And so when you see these, there's room for concern when you see this, but it doesn't mean that the entire sample chain is bad or anything like that. As you can see, the ESS isn't too bad. We get something that we run 1,000 iterations, and we get something that's like close to 500, like half of them are useful. And as we can see, we recover the true parameters for beta, alpha, and beta super. The in pi, not so much, and this might be due to the numerical issues. This particularly could be quite sensitive. And then we sample, and then we run stereo checks. we get a bunch of plots. Yes, so here we can see, and now at least we're capturing the zeros pretty well, which is good, because that was the big issue from the previous models, simpler models. And as you can see here, now the posterior predicted distribution aligns much better with the true observations. I think this is it's missing its stats fronts, but this is going to be very small, so let's not even run it. Yeah, here you can see the retrogram again, which is obviously the expected counts align very well. And yeah, finally the intervals again much better corresponds. You can see that the true observations actually fall quite nicely within the samples from the posterior predicted. Though it's still there's a bit of discrepancy, but it's not as bad as it was before. And yeah, the next thing here is that we sort of haven't considered adding using the fact that these data are like the traps that we have as clustered by building, and so it might be useful to sort of add the fact that all these different constraints that we have, which building are they coming from? So this is what we're doing here. So we might do some. So we want to check that to see if there's possible there is some relationship between them. So that's what we're doing here. And yeah, as we can see, there seems to be. Let me see. Like, what is this plot, Kirsty?
What did you say?
What is this plot? This is what the variation cost building.
So it's
yeah.
This is means of the by building.
Yeah. So you see the building IDs is the title here, and then you can see sort of the actual mean, which is the black bar or the dark bar, and then you have the mean of the buildings under the posterior predictive, where we can see that there are some of them where the distribution of the sort of the posterior predictive given a certain building doesn't really align well with the true sort of mean of the different mean of the complaints in that specific building. For example, number 70 and number 45 kinda, number 47 not so much. And so this indicates that they might be useful to sort of add in the building data to the model and attempt to try and capture this last discrepancy here. And so that's what we're trying to do. I'm just checking something here. Okay. Yeah, this brings us to the last tutorial. And yeah, as we said, now what we do here is we add a hierarchical intercept parameter, alpha, which is per building at the building level. And this will be an intercept, so it won't depend on the underlying. It won't be conditioned on the. We have one of these for each of the buildings.
Yeah.
So in our stand model is false. This is not a stand model, but yeah, okay. Yep. Because do you want to say something?
No, basically just we want to have like separate or have more separation or like different accounts for buildings, or we want to so not much to add except other than that. So we just add a building specific intercept term.
Yeah. So we have this now, and this is not a fixed parameter. It's sampled from a normal with a particular variance and an alpha. So this is what we're doing. And is there anything more? The average of ongoing runs we add.
Yeah. So now we need to like massage the data a bit to get this. We have this matrix that has building specific. There's 10 buildings, and then we have like building specific regressors or like properties that are like properties of the buildings. So we have if the there's a superintendent living in the building. What's the age of the building? Average tenant age, and average rent. And then now we built this linear model for, what did we do?
Yeah, it's a log linear model.
Yeah.
I see there's a question. Bill asks if, does Turing allow the user to access the cumulative log probability? Yes, it does. So in Turing, you have written a model like this, demo, You can access it. So in Turing, we have a bunch of internal objects. So there's this thing, which is the sampler, and then this var info. Var info is the trace structure in Turing. Generally, you don't have to access these. But if you want to add a custom quantity to the log probability, like the log joint, which is often something you might want to do, either just to make things more efficient, or you have some custom quantity they want to add, then you can use this Turing.add log. I need to use Turing first because I haven't done this yet. But you can use this add log prob macro, and then whatever you write here, the expression, say 1, that will be added to the log prob. And this is particularly useful if you want to make something more efficient, or if you want to add some missing constants, something like that. Not missing constants, sorry, but missing expression to it. Hopefully that answers the question. And someone is complaining that, they're asking if it says that the video quality is 240p, and they're asking if that's the...
They said that you slow down your scrolling because it seems that.
Okay.
Yeah, so.
Okay, so here we see the data matrix. As you can see, there's 10 buildings, and then we have five addresses for each of the buildings. And yeah, it's not the full hierarchical model. We're going to use a half normal, which is just a truncated normal. So in distributions.jl, what you do here is you take it truncated, and then you give it to the unimath distribution. So here, this is just a convenience constructor.
And that's just because we want to have positive values for sigma, because that's the variance, or that's a standard deviation.
Exactly. And we also just added, instead of making it 0, we make it very, very small, just because they can sometimes lead to numerical issues. Not in sampling necessarily, but maybe only sampling from the prior, possible. And this is the same like the Binomial as we used before. Nothing particularly interesting there. And so now we have the building data as the additional data point. We still have the complaints that is missing, and then we have all these other arguments. And also note, we keep using keyword arguments. This is to be consistent with the other tutorials, and because it's quite nice, because it means that we can sort of, oh yeah, it's not implemented. Okay. We can also, yeah, it's just kind of quite convenient. You can also just provide them as arguments. So for some reason, I don't have the solutions.
No.
Oh, okay. Well,
one more point to that, the keyword arguments. So yeah. We were discussing which SOS might have add tuple traits later. So then you could use any kind of tuple source. So you could use pass like a data frame to your model, and then it would just extract the corresponding columns, or get the correct variables there. So if you'd had to have a data frame with traps and live interval, then you could just pass the data frame, and then it will use the correct columns.
Right. Yeah, we need to add connections to some of these other interfaces, tables and table traits, and yeah, I think that will be great for expanding the functionality of that.
Yeah, cool. Yeah, and someone says, can't run any of the different model notebooks, my kernel keeps dying. There's probably some dependency. It's difficult to debug from here, unfortunately. But it might be some dependency. Make sure you're running the correct Julia version. It needs 1.61 or higher. Yeah, maybe we can probably help with that some other time.
Yeah. I plan on making this a lot cleaner, because this was really rushed. So it's a bit buggy, and as you can see, it's there's a lot of issues. But I plan on making them a lot cleaner, and then finishing the rest of the notebooks, or the time series one, and then you can use it easier.
Nice. So yeah, because we didn't cheat, we're just that clever. This is the solution that we should have here. And so this is just, as I said, sampling the mu from a normal, and then we have the alpha as the intercept, and it's building data multiplied by this theta that we sampled here, which is just a sort of a IID, KIID normals. And we have the sigma mu that is also sampled. So we added these, the alpha we already had from before, we added this parameter, which is K's parameters, and then we added this parameter, and now we're sampling mu from distributions under these. We have, and then eventually the U rate makes it into the model here, where we have the building indices. Note that for those who are familiar with Julia, so I'm broadcasting over this entire expression, meaning that we put dots everywhere, and it's all applied element-wise. And this includes, and so what you end up with is sort of just a bunch of dots in all of these expressions. And in this mu here, we're sort of indexing by building index. And so mu is a vector of k, I suppose. So v of k. And then the building index is actually a much longer vector of indices, which runs from 1 through k. And so this is just sort of, this will also, even though this building index is like 120 length or something like that, this will just sort of expand.
Actually, it's here it's the mu is a vector of j, I think, because it's the number of buildings, and there's 10 buildings, and the j is the number of rows in the matrix. So that's
makes sense.
Yeah, but yeah, it's
because say that's k, and then building is jk, and then you multiply them 2, and then you get j out. Makes sense. Yep. And so we instantiate it as before. I keep adding, just like as people are aware, I've sort of kept adding the parameters to the return value of the model. As I said, this could be arbitrary, but it's very convenient for when we're doing this sort of explorative stuff. And then we transform the data, we add the total square, this like log again, and we condition on the data, and we sample, as we did so many times before. Also, if people notice this, we are clamping some values here, because this doesn't really matter during sampling, because the sampler will look for high regions with some some probability mass. But under the prior, which kind of tells us that the prior is probably a bit too flexible, but under the prior, it is possible to get very large values that can lead to numerical errors. And so we just sort of clamp at these unreasonable values by itself. So there's saying that the mean can't go completely to 0, and is saying that we can't end up with more than 10,000 cockroaches in one unit, which I think is, I've never been in New York, but I think that's reasonable. Maybe not in New York. So we're sampling. It takes a bit to the initial one, because we need to compile stuff. And so now we're actually getting to the more interesting parts of the entire tutorial, which is diagnostics. So what we'll do now is sort of do proper analysis. Now that we have a model that can sort of reasonably fit the data, we then start asking, like, okay, but are the samples actually coming from the right distribution? Are we sort of getting a good number of samples? Is the sample being efficient, and so on? And so so we'll just look at the posterior here. Kirsty, you wanna?
Yeah. So we'll see that the main issue here is because when we're using Hamiltonian Monte Carlo, we're exploring the gradients. So depending on the parameterization of the model, it can get stuck somewhere if there's like sort of kinks or like cracks in the distribution sort of. So the idea of these diagnostics is to look at or see if the sampler gets stuck somewhere because of the geometry of the posterior. So if we can detect that there's some problems, then we possibly can reparameterize the model so that it's easier to sample from, or like the sampler will not get stuck.
Yeah. So here we did the immediate thing we see here. Though, remember we did 1,000 iterations per model, and before when we ran the simpler models, the effective sample size, which I sort of explained this as kind of how many independent samples we get from these 1,000 iterations, it was actually pretty okay. It was sort of 250 at least, which is more than enough when you're doing something simple like that. But now that we have a larger model and more complex model, you see there are certain parameters which have an ESS of 65, for example, or 64, out of 1,000 iterations. And that is that ESS is, of course, very heavily related to the autocorrelation between each of the iterations. And so when you see something and ESS is quite low, it does give you an indication of exactly what Kirsty said, that sort of there are certain parameters where you kind of get stuck, where you end up proposing a new value to move to, and then you would reject it because the sort of the joint distribution changed so much in the proposed at the proposed value that you end up rejecting it because you have this metropolis-hazing step in the. But this is not, and also what pointing out is not just for gradient based. This will sort of happen if you just run regular metropolis-hazings, that once you get to these high curvature regions, making proposals, either you have to make proposals very, very close to where you're currently at, or you have to, or you're going to end up sort of rejecting the proposal. But if you start making the step size so small that you accept the proposals, then you're kind of not even moving around. And so we want to try and avoid cases where the bus areas are like this. So here we see that there are some issues, and it's a question of how to address them. Yeah, this is what the text is saying, I suppose. Yeah, so you see the effective samples are somewhat low for many parameters relative to total number of samples. So we look at, yeah, it says it doesn't. Okay, this will be a super small figure again, which is unfortunate. So we should I'll is using the always one instead. This takes a bit because this is the famous first time to plot in Julia, which is unfortunately a bit longer than it needs to be. But again, here we just call these two Arvis function to convert. We give it the prior model, and we give it the condition model, and then we give it the posterior samples, and we get back this inference data frame that we can then sort of use to inspect the posterior and the posterior samples that we have. So in particular, we'll look at the sigma mu, as we saw earlier. Sigma mu is one of the parameters that have one of them has quite low ESS. But you see the alpha is actually quite low, but sigma mu is also quite low. And we'll look at this in particular because it relates to, this is sort of there's certain relationships we want between the sigma mu and these mu's. So yeah, here you can see a very, very small density plot. I'm still very confused why this happens. This does not happen when you don't do it in Jupyter Notebook. Yeah, so here we're internally sampling from the priors, sampling from the, then we're sampling the predicted distributions, and we get back a trace plot eventually. This is also here after I've gotten that. Here's some code that we will then use to plot these corner plots that I will show you in a separate tab because of how slow this is. Not how slow, because how small these end up being. Maybe find it. That's quite an output. Oh, nice. So yeah, as we can see here, we have the posterior zone, and we plot the trace. And notice these black bars here. These blacks indicate that we have numerical. These have numerical errors, and it might be difficult to see from the YouTube video, but you might see that where we have a lot of numerical errors, you see the sigma mu is getting stuck. It's not really oscillating a lot, and then suddenly start oscillating, and we don't have enough numerical errors, and then we have numerical errors again. And so this keeps on sort of happening throughout, indicating there are regions for which sigma mu behaves poorly. And this is a particularly bad coloring of this plot. But you can see this clustering behavior here, where we sort of have a bunch of this relationship between the log sigma mu and the mu form. As you can see here, this we sort of have the points here looks almost like a cloud, a point cloud. It is I can't make it larger, unfortunately. But as we'll see later, that this is actually kind of not what you want to see. It turns out the posterior is not quite like that. We'll get to that. So here you can see the trace plot, as I said. There's a very, very, very small plot. We can, so as we said, like this has like cloud shape. And the reason why we this sort of tutorial is saying that you expect a funnel like a funnel rather than a cloud. And the reason why you can sort of suspect that already, though it will be made more clear later on, is because you can see this plot. Oh yeah, I'm looking at the wrong one now. So you can see this is what I'm talking about. It's because under the prior, we see a somewhat different behavior. Man, Chrome is not liking me zooming this much. But this is under the prior. So here we sampled under the prior and plotting the sort of correlation between them. As you can see, this actually got this kind of funneling behavior. And so you would sort of expect it to be follow something, have like this is similar correlation, even though even though the posterior will be different, you sort of expect it to have a similar correlation. At least in this case, apparently. And yeah, we can also plot sort of the parallel plot, which is between sigma and mu. This is quite nice because it essentially shows us where for small values of sigma. So all these black lines, these dark lines are non-divergent divergent transitions, and then we have the orange lines, which are divergent transitions. As you can see, for small values of sigma, we end up with the divergent transitions very, very often. So it indicates that there are some issues there. That probably could be.
I'll add a bit about the divergence, or basically just where the name comes from. So in Hamiltonian Monte Carlo, when you're like basically moving around in the joint distribution, or like in the PD or the density of the joint distribution, you're using the gradients, and it's like a sort of physically inspired thing. So it's hence the name Hamiltonian, and you're using a differential equation to solve the path of where the particle is moving, and if the ODE solver diverges, so basically it means that the geometry is like changes too sharply, that the solver is not keeping up. So then it's like diverging from the actual solution, and then we can plot the diverging particles. And if here we see that there's a lot of diverging particles for small values of sigma, and do we have like some kind of plot for the funnel, or do we have to?
So that this funnel, you mean?
No, I mean if you look at the model, so it's wait, because there's like I guess it's a bit difficult to explain without the plot, but wait. So there's a dependence of the parameters, so that basically there's the geometry of the posterior is like funnel. So the I don't know how to explain it. The posterior is really, there's a really sharp corner in it.
We'll see this this later.
Okay.
The funnel, like the sort of exemplification of the other funnel.
Good.
Because as I showed before, if you could see it, there was like, this is from the prior, but there was like a cloud formation rather than this funnel-like behavior that we see here. And we'll later see that if we do reparameterization, which achieves better ESS, and so we can sort of be confident that it's, and also other things, is we can sort of be confident that it's going to replicate the posterior better than this particular one. We will see that it indeed has like this funnel structure. So that would be clear. But also, so this is the thing, the divergences, as Christy explained, is related to the integrator being used in the Hamiltonian sampler. And NUTS, it will try to adjust the step size used in this numerical integrator to sort of address the fact that you have sort of a high curvature in your geometry, in your sort of distribution. But it can only do so much, and there's it does this globally, meaning that there are still certain regions where it can still behave poorly, as we sort of see here with the ESS being pretty bad. So, but this can also be addressed, by the way, we ran it for 1,000 iterations. And I think we end up with, as you can see, it says iterations 500 to 1,500. What we really ran it for is 1,500 iterations. 500 first iterations are actually adaptation, where we sort of changing the step size to sort of adjust to avoid these numerical divergences and so on. And so you could try and address this by simply running it for longer. So have more adaptation steps in your nuts sample if you wanted to. But we'll try to demonstrate something else there, so we're not going to do that. But yeah, so this is the divergence plot. And so the idea now is that we're going to reparameterize the model. This means that instead of writing it like this that we did above, we're going to write it as instead of sampling the normal, the sigma, this mu raw here, we're going to sample the standard normal variables. And then we're going to shift them and scale them accordingly. So we still get this distribution for mu, but instead what the sampler will see is these sort of easier to handle variables, because these are then just samples from a normal distribution. And oftentimes you find that doing these called reparameterizations can help quite a bit. Because this means that when we're doing this adaptation in the beginning, it's particular for nuts, this generally has this sort of parameterization generally has a simpler geometry to deal with, and so it's easy to construct to adapt the parameters of the sampler so that it will work well on this particular instance. Christy, anything you want to add?
Not really. That's the main takeaway.
Yeah. And other than that, there's nothing new here. So everything else is the same. Literally, the only thing we do is that instead of sampling the mu directly, we sample mu raw, which is just standard normal, and then we compute mu as this instead. So we can sort of run this and sample from it. Again, conditioning on the data, everything is as usual. Still using 1,000 samples, so I'm not trying to cheat there. Yeah. And so why the samples? As you can see, it works. And yeah, now we can check whether or not it actually has an improved anything, or if it's still pretty bad. So, oh yeah, I'll show the chain. Because the Poisson MCMC is the one that's the non-centered version parameterization. As we can see, the ESS is much better. So remember, for alpha, for example, we had 64 before. Now we have 450, which is a significant step up. And this is good. This is good. And yeah, and so there's a bit of code to sort of plot essentially the same plot as we had before, but now because as it is in Turing, like because this mu is now a computed quantity, it's not a directly sampled, right? Now we have access to you look at the chain here, there's no mu, there's only mu raw. But because we're returning mu in the return statement here, we're still returning mu, we can still obtain it. So we can sort of execute the model, get the return value, but we can condition it on the chain that we just sort of obtained using sampling. That's what we'll do. Just take a bit of code to sort of to work with it afterwards. This is calling generated quantities. It's sampling and getting the return values, and it's using conditioning on the parameters in the chain that we got before. So if you do this and plot it, I'm going to show it here because it's super small. So I'm going to go to this cheating stuff that we have here. I'm going to open this. And if you compare this to the previous plot that I showed before, you see this has like a funnel-like behavior rather than a sort of clouding around the end there. And so this is kind of, and given that we have better ESS and so on, we can sort of be more confident that this is better, and okay, not just the ESS, we also have less numerical errors and so on, that this is actually a better representation of the area. And so we see this funnel-like behavior we didn't see before. So that indicates that our reparameterization actually did something useful. As you can see, the black bars there, there are only 3 of them. Whereas before we had a bunch of regions where the sort of sigma mu got stuck. We can probably look at this here. So this is the before, how we had certain region where completely stuck and so on. This is no longer the case. And as you can see here, we have this sort of this parallel plot, which shows us the numerical divergences of the thing. And again, much fewer. There's only 3 of them now. This is good. This is exactly what we wanted to achieve by the reparameterization, and it worked, which is nice. So we can sort of do the same predictive posterior test that we did, posterior predictive test that we did before. So we can sort of get some analyzed outputs there. Now we can see that we have a pretty good estimate of the true parameter, the true sort of data, compared to what we started out, which was pretty bad fit. That was all the way over here. Now we can also, since we also recently included the building data, we can now look to see how well calibrated our estimates are here. And as we can see now, this is sort of matching the means given the building IDs very well compared to what we had before. So all it's just the wins everywhere. And this is just matching the standard deviation rather than the means. And as you can see, it does a pretty good job, except for this particular building. But in most cases, it does a pretty good job now. Those predictive intervals, as you see here, again, you can see that it does a pretty good job. Like things are improving significantly versus what we had before. The rootogram just showing the same thing once again. And yeah, finally, brings us to the very final point, which is the varying intercepts and varying slopes. So for this, we're going to use a slightly larger data set. We'll load in here. And now we're going to add in these. So now we have these kappas here. We have this building data that was before, and now we also have these kappas for the buildings. But this is using, what's the gamma here?
Do you have the model? Where do?
So I have the model. I'm trying to see what's the gammas. They're using building data, but they're using. We have. Yeah. So the mu are the intercepts. So both of these are building data.
Yeah.
Right.
So basically we have like a linear regression for the intercepts, and then for the slope. That depends on the buildings.
Yes. So before, this wasn't dependent on the buildings, and now we have a coefficient that's also dependent on the buildings for this thing. Essentially, just adding more complexity to the model. And if you're running this yourself, you should implement this. But we're a bit too lazy. It's been a long day. So we're just going to copy paste like proper programmers. I'm just going to remove these there. Make sure everything is okay. Yeah. This one, conditional data sample. We plot sigma. Now we're hoping that we're going to be able to do a slightly better job. As we saw before, the fit was pretty good. As I just want to mention this again, I'm reading this together with you guys, okay? So I'm trying to figure out what we're interested in modeling here. Because do you know? There's a massive small center, so we usually in a hierarchical. Also notice that we just went with the kappa raw immediately, right? So in the model here we had the same thing as with mu, but now we just didn't even bother. We just went for the reparameterized version immediately. So we're computing kappa raw.
I guess it's usually when you have the sigma is or the standard deviation of the normal is a pretty common place to have the funnel.
Yeah.
So that's
I do want to mention that this is the case, but I've been working with some models recently, which are very high dimension, and there's essentially convolutions involved. And if you give it enough steps to adapt, you still get pretty good results. You also generally, for most of the questions you want to answer, you don't really need. It really depends on what you want to answer. You don't need, for example, 1,000 independent samples to be able to answer a question. But if you want to look at the correlation between two variables in particular, then you need to be careful, as we saw earlier, right? You can give it sort of false sense. So it depends on what questions you want to answer, really, when you're talking about this. But generally, it's always a good trick to sort of do these reparameterizations, for sure.
And
so
I will.
So
there's a wiki, or like Stan has a wiki for like common reparameterization tricks. So it should be in the references in the repo. But if it's not, I'll add it there.
Yeah. As you see, the ESS is still taking like a hit. There's some parameters that are 200, but it's still decent across the board. There's no sub 100 that we see here. And we can pause here, plot these again. It's again, unfortunately, very small plots. But here you can sort of see, like, so this also, in general, we don't need to use the plotting stuff from RViz and from ggplot. We can really just use the sort of stats plots, and there's a good integration with it. But just for some reason, it's kind of messed up at the moment with in the Jupyter notebooks. But yeah, then we can sample. Okay, so this was a typo in the model. This is a nice thing here, is that we're not tied to the model. So even though we sample it from a particular model, and now we rerun it, now we sort of rerun the model and redefine it, we can still use the same theory that we have in the other chain. I forgot to add like a default value for one of the parameters. Finally, we plopped all these posterior predictive chains that we checks that we did before, and we can see whether or not this adding of the kappa made any sense whatsoever. And now this is a new data set, so you can see we have more data. And so I'm guessing that the guy who originally wrote this tutorial, the reason why he suddenly included more parameters was because the previous model that we used didn't really fit this large data set particularly well. Yes, we do this thing where we look at the buildings again, make sure we sort of have well-calibrated predictions for this. It looks pretty good. Same here, good for the standard deviation. Again, it's very, very nice. And finally, the interval plots, that was pretty good, and the rotogram. Yeah, and I think this sort of have taken you through a very, very hasty and very chaotic introduction.
Yeah, hopefully you got something out of it. Yeah, I'll clean the notebooks up, and it should be better.
Yes, sounds good.
Yeah, that's about it. But if you have any questions, you can like ask me directly in what I prefer Zulip, but then you can also like raise issue in the repo or make pull request or anything. Yeah.
And then again, sorry for
anything you want to add.
I mean, yeah, sorry for the chaotic and unpreparedness. There's a lot of technical issues in this. This is how it goes.
Well, I think given the technical issues, we all owe Tor a huge thank you for jumping in and saving us with being able to walk through the notebooks.
Yeah, and actually coding them up.
It was a busy yesterday.
Yeah.
I was thinking I should just make a PR and add Turing stuff. I mean, why not? It would be nice to have them there.
Yeah.
I was not expecting this, but
it's fine. You definitely saved the workshop. Yep.
It was good, man, and it's pretty cool tutorial. So even if you didn't enjoy this one, you should check out the original one.
Yeah.
Cool. Last question from people. Any Chad? Do you wanna add something?
Yeah, I don't know. I really like the examples here, and the being able to walk through the Turing, I think, is really great. There were a couple of small glitches with the sauce version, so I'm really looking forward to getting that into place and having that available as well.
That seems good.
Also, there was one question about actually merging sauce and Turing. So I want to say that we don't have plans to merge them as such, though that's potentially something that could happen in the maybe more distant future. But we have had a lot of discussions about being able to use one package with the other, and ideally we really want this to be. I think we all want this to be something that you can sort of mix and match, kind of as you go. When you need this or that capability, to be able to just kind of pull in the tools as you need them.
Exactly. Ideally, even though it's unlikely that Turing and SOS will become one package, at least we're really working towards and hoping. So we're trying to collaborate and make it so that we can reuse code, as Chad said, but also at the very least, the users shouldn't sort of have to worry too much. They can sort of pick and choose essentially. That would be an ideal world. Yeah. Yes. Cool. Kirsty, you want to take from here?
Yep. I guess that's it. I'll just end the broadcast.
Cool.
Thanks for attending, and thanks Tor and Chad for helping me with the workshop.
Thanks, Kirsty. Thank you all.
Bye-bye.
Bye.